Welcome to today's explainer. We are jumping right into something I find absolutely fascinating, the invisible currency of heat. Have you ever stopped to think about how scientists actually measure thermal energy when, we can't even see it? Well, it's done by building what is essentially a perfect thermal vault. Today, we're going to explore the brilliant logic of calorimetry and break down the exact science of how liquids and solids exchange body heat.
Let's get right into it.
Here's our quick syllabus for this virtual lab day. We'll start with the rules of heat exchange, head inside the calorimeter vault, test its capacity, and then measure liquid and solid body heat before calculating our final results.
Okay, Section 1, the rules of heat exchange, understanding the invisible currency. So let's dive into the foundational rule of calorimetry. It all rests on the principle of energy conservation. In a perfectly isolated system, the lost heat plus the received heat always equals zero. It's a beautiful concept, really. Inside this perfect system, no energy is ever truly lost. The heat given off by one object is completely absorbed by another.
But how do we actually calculate that exchanged heat? Well, it comes down to two key concepts. First, we have specific heat. You can think of this as a program measurement. It's the exact amount of heat needed to raise just 1 unit of mass by 1 single degree Celsius. Then, looking at the other side of things, thermal capacity applies to the whole object. That's the heat required to raise the entire intact body by 1 degree, totally regardless of its mass. Notice that in both equations, we're multiplying by the difference between the final and initial temperatures. That difference is key.
And just before we get our hands dirty with the physical experiments, we should also briefly note that our invisible currency of heat can actually be spent in another pretty cool way. Instead of just raising an object's temperature, heat can be used to change its physical state completely. We call this latent heat. So whether we're talking about the latent heat of fusion, melting a solid into a liquid, or evaporation, turning a liquid into a gas, something wild happens. During these transformations, the temperature actually stays perfectly flat while the physical state is changing. It's like the energy is entirely focused on breaking bonds rather than heating things up.
Moving right along to Section 2, inside the calorimeter vault, creating an adiabatic enclosure. To measure all of this accurately, we need the ultimate game board. I'm talking about an adiabatic enclosure, a space that completely blocks heat from escaping into the outside world. Now let's look at how this impenetrable thermal vault is physically constructed. We've got an insulating wall and a super secure lid. These are strictly designed to prevent any heat exchange between the inside of our little universe and the outside laboratory air. Inside this vault, we have our calorimetric liquid, an agitator to make sure the temperature stays nice and even, and a high-precision thermometer. This whole setup is what lets us perfectly measure the heat released or absorbed during a physical phenomenon.
All right, so here are the raw materials sitting on our workbench for today's analysis. We have our thermal vault, the calorimeter itself, plus our heating elements like the bain-marie and hot plate. We've got precision measuring tools like a scale and our thermometer, and finally our 3 test subjects, everyday water, ethanol, and a solid metal block. Though just a quick dose of practical lab reality before we start pouring things, the thermodynamic math we're doing here is flawless. But our very expensive glass thermometer? Yeah, definitely not shatterproof. We absolutely must avoid sudden physical impacts or massive instantaneous temperature spikes, unless you really want to explain to the lab director why we need to buy new equipment.
Okay, Section 3, testing the calorimeter's capacity. Experiment 1, which is calibration. See, before we can measure unknown substances, we have to run an initial baseline test to measure the thermal capacity of the calorimeter itself. Every single piece of equipment absorbs a little bit of heat, and we have to account for that using hot and cold water.
These exact steps act almost like a high-stakes cooking recipe. We start with 100 milliliters of cold water acting as our baseline right inside the calorimeter. Then, we take a completely separate 100 milliliters of water and heat it to exactly 60 degrees Celsius. Now, step 3 is the make-or-break moment. We have to quickly pour that hot water into the calorimeter to ensure our heat currency doesn't just evaporate into the room before the vault is perfectly sealed. Finally, we shake the whole mixture up and wait for it to settle in a new, unified equilibrium temperature.
And this completely illustrates the math happening in real time. We start with our initial state. The hot and cold liquids are totally separate, and that tight seal means absolutely no heat is escaping the box. Then, after mixing, the hot and cold states have entirely merged until a single, steady thermal equilibrium is reached. The heat lost by the hot water was perfectly equal to the heat gained by the cold water and the calorimeter walls. Our foundational equation equals exactly 0, just like we wanted.
On to Section 4, measuring liquid body heat. Experiment 2, testing ethanol.
Now let's see how our math holds up when we introduce a completely new, totally different liquid into our newly calibrated system. The procedure here is remarkably similar, but the values are definitely different. We take just 5 milliliters of ethanol and heat it up to 45 degrees Celsius. We pour this straight into our insulated vault containing 100 grams of cold water, agitate it, and wait for equilibrium. By tracking exactly how the ethanol's 45-degree heat transfers into that cold water, we can mathematically isolate the unique heat capacity of the alcohol. We're essentially mapping out alcohol's specific thermodynamic fingerprint.
That brings us to Section 5, Measuring Solid Body Heat. Experiment 3, the heated metal. For our final test, we're swapping liquids for solids to observe how a dense metal block releases its thermal payload.
First up, we weigh our metal part to get its exact mass. Then we place it on a hot plate, but unlike the liquids, we crank the heat on this metal surface until it is well over 100 degrees Celsius. Using a pair of pliers, because obviously, we plunge this scorching piece of metal straight into our 100 milliliters of cold water. Because the temperature gap is so massive here, we actually get to observe a rapid, pretty violent thermal exchange.
This right here is the ultimate proof of our thermal vault. That intense heat radiating off the metal is perfectly trapped by the water and the insulated walls. Slowly but surely, the metal cools down, the water warms up, and they meet right in the middle at thermal equilibrium. It's physics in action.
Finally, Section 6, calculating the final results, the final tally. With all 3 of our experiments wrapped up and our equilibrium temperatures properly recorded, it's time to actually exploit those results. We crunch the numbers using our conservation of energy formula to calculate and then rank the specific heat capacities of our materials. When we place these calculated values in ascending order, we reveal a pretty incredible fundamental truth of nature. The solid metal has the lowest thermal capacity. That means it takes very little heat to change its temperature. It heats up and cools down super quickly. Alcohol sits somewhere in the middle. But water? Water is wild. It has an incredibly high thermal capacity. It takes a massive amount of energy to heat it up compared to dense metal. Which actually leads us to a pretty profound realization. If everyday water requires so much energy to heat up and holds onto that heat for so long compared to solid earth and metals, how does that invisible property shape the climate of our entire planet? I want to leave you with that powerful thought today. Connect our micro-level calorimeter lab results to the macro-level oceans that absorb the sun's heat and literally regulate the temperature of Earth itself. The laws of thermodynamics we just explored in a tiny glass vault are the exact same laws keeping our world habitable. Thanks so much for joining me on this explainer, and keep asking great questions.